Example number 3, which I like to affectionately refer to as the Uber relative motion question. At first glimpse, this question appears to be very, very complex. But if we follow the technique that has been outlined in terms of creating the vector equation and using the notation that has been shown in the previous examples, you'll see that this question actually isn't as bad as it appears initially. Let's start off. A pilot is flying with an airspeed of 500 kilometers per hour on a heading of north 45 degrees east when he notices another plane approaching on radar coming from the west at a rate of 100 kilometers per hour with respect to the first plane. If the planes are flying through a 75 kilometer per hour southerly wind, find the second plane's velocity with respect to the ground. The hardest part for students approaching a problem like this is being intimidated by the sheer amount of information. The best approach when working on a problem like this is to break it down into the initial steps. Don't try to solve the problem in your head yet. The first step is to extract the information and then figure out what the question is asking. Part of this, however, is having a good sense of creating logical notation. So let's start off with highlighting the key information. So we know we have a pilot flying with an airspeed of 500 kilometers per hour on a heading of north 45 degrees east. So one plane is flying this way, our initial plane. Our pilot then notices a second plane approaching on radar coming from the west. Now, if it's coming from the west, that implies that it is traveling towards the east. And that's an important thing to be able to parse. The difference between coming from as opposed to moving toward. And we have a rate of 100 kilometers per hour. Now this is important, it's with respect to the first plane. So the second plane's motion is being described in terms of the first plane. So when you see this, we need a way of distinguishing between the first plane and the second plane. What I suggest is not using the numbers 1 and 2, but using a letter convention. So my preference is I use A and B. So I'm going to refer to the first plane as A and the second plane as B. The next little bit of information. Both of these planes are flying through a 70 kilometer per hour southerly wind. Now remember, when we see southerly, that means coming from the south. This implies that the wind is moving towards the north. Now the thing you have to remember, that wind speed or velocity in this case, because it is given a direction, it has to be measured in reference to something. And the wind is always measured in reference to the ground. So that 75 kilometers per hour is the wind's motion relative to the ground. And finally, what we're looking to find, we're asked to find the second plane's velocity with respect to the ground. So now that we have extracted the information that we have and identified what we're looking for, now is the time that we start filling in the given information. So as mentioned earlier, I decided that I'm going to use the letter B to represent the velocity of the second plane. So the second plane's velocity with respect to the ground, that would be BVG. The second plane, B, velocity with respect to the ground. Now, one of my issues here, I didn't mean to scratch that out, I meant to highlight that, is the tendency for me to have my subscripts creep up. They really should stay as subscripts. Okay, so this is what we're looking for, BVG. Next, let's start identifying the information that we were given. So a pilot is flying with an airspeed. So our first plane is moving at 500 kilometers per hour on a heading of north 45 degrees east. So we have the letter A to represent the first plane and V for velocity. But what is it in reference to? The key word, airspeed. That means it is measured in comparison to the air. Well, when we talk about the air, really we mean the wind. So I will use the letter W to represent what it's in reference to. So this is the first plane's velocity with respect to the wind. So A representing the first plane, velocity with respect to the wind, and we know that that is 500 kilometers per hour to 3 sig figs, and that is north 45.0 degrees east. Let's zoom in a little bit here. Now the second plane. The second plane is coming from the west, which means it's moving east at 100 kilometers per hour with respect to the first plane. So the second plane, B's velocity with respect to, and again, the first plane, so this would be BVA, is equal to 100 kilometers per hour and moving to the east. My notation's a bit terrible here. Okay, so remember, coming from the west means going to the east. And then finally, we have the wind's velocity with respect to the ground. So the wind's velocity with respect to the ground is equal to 75 kilometers per hour north, because southerly means that it's coming from the south, which means it is moving north. Great. So here's what we got. We've got good notation and we're consistent. So we didn't change our letters in mid-through, because one of the tendencies is to see the word airspeed and want to use the letter A. And then obviously you'd run into the problem of AVA. You can't have that. So that's why we decided to use W. And that's generally what I use. I use W to represent the wind as opposed to the air, A for air. And then of course, we were consistent in terms of referencing the ground. So that's good. So we don't have any rogue additional notation. So now what do we do? Well, the next step, of course, is we need to establish our vector equation, because the vector equation is going to inform us how we're going to draw the vector diagram. And then from the vector diagram, that will inform us on how we're going to solve the problem step by step. So don't try to go to the final part of the solution. Work on it one piece at a time. There are going to be times when you're going to have to solve a problem where you don't actually know where you're going with it. The key is just keep going. And you have to follow these best practices with these techniques. This will give you the future insight onto solving these problems. And the more problems you do, the faster and the more efficient you become at them. So we're going to start off with our vector equation. So we're looking for BVG. So let's start off with BVG. So BVG. Now, again, we start with the letter B, which means we need to start with, on the other side, the first vector also has to start with the letter B. And in this case, we've got BVA. So BVA. Now, the next vector has to start with the letter A. So we end with A, the next vector has to start with A. So when we look at our given section, well, that would be AVW. So the next vector is AVW. Now, the next vector has to start with the letter W. So we go on our list and perfect, WVG. And we have run out of vectors and hopefully we got to the finish line. And the good news is we have our final vector ends with a G, which is perfect because our initial vector also ended with a G. So BVG is equal to BVA plus AVW plus WVG. It works out. Our vector equation makes sense, and then we can move from there. The next step, we're going to give short names. So BVG is our resultant. BVA is our vector A. AVW is our vector B. And WVG is now our vector C. So let's modify our givens to reflect that. So BVA, that's our vector A. AVW, that's our vector B. And WVG, that's our vector C. And BVG over here, that is our resultant. Actually, we'll just write it as like that. There we go. Perfect. All right. So now when we look at this, we realize that we're not going to get a triangle out of this. This will make a quadrilateral. It's likely that BVG will not be 0. So when we have this situation, we automatically know that we should use the component method. So we can draw the vector diagram and then do the component method. But generally speaking, when you see that we have a 4-term vector equation, immediately we go into component method. But for the sake of review and just to get a sense of which way our vectors are going to go, it's actually not a bad idea to draw the vector diagram first and then the vector chart. But generally speaking, I personally just jump right into the chart anyway, with some notable exceptions, of course, and that will be in the next questions where it gets a little bit more complex. Now, the reason why we can jump right into the vector chart is because we know everything about all the vectors that we have. We know everything about vector A, B, and C, unlike some of the previous examples where we didn't have that information. So let's draw our vector diagram. Now, of course, when we're planning this, it's important to start in a spot that makes sense. So now when we look, we know that our first vector goes east, then our second vector goes north 45 degrees east, and then our final vector goes north. So it doesn't make any sense to start here at this point because we'll run out of real estate. And since there is no western motion, we can start on the left margin. But we do know that there is a lot of motion towards the north. So we should start a little bit lower and on the left-hand side. So our first vector, A, is 100 kilometers per hour east. So there's our vector A. Now our vector B is north 45 degrees east, which means we need to put in a compass rose. So there's our compass rose. And our vector B is the longest, and that should be represented as such. Now, based on where I started drawing my diagram, I feel I'm going to run out of some real estate. But since I'm doing this in OneNote, it'll be fortunately easy to get away with. All right, so let's move this down a bit. All right, so we got our vector B, and it's north 45 degrees east. So we'll put in our 45 degrees right there. So we drop in another compass rose. And now our vector C, which is 75 kilometers per hour and north. So that'll be the shortest of the three vectors. And now we have our vector C. Finally, let's draw on the resultant. And the resultant starts from the tail of the first vector to the head of the last vector. So our resultant, and this angle down here would be our theta r. Now, one thing to note, it looks like R and B are parallel to each other. And that's likely because of the poorly way that I drew C. And I kind of look at it now and C appears to be about the same length as A. So we really should clean that up a little bit. It's a little bit better. Okay, so the expectation is that our resultant is going to have a north and east component. And by the looks of it, the magnitude of our resultant should be the largest compared to vectors A, B, and C. So vector R should exceed 500 kilometers per hour, and it should be moving north and east close to 45-ish degrees. And based on what vector B is doing, R should be less than 45 degrees. So if you kind of look at the diagram and you judge it based on that, depending, of course, and assuming that you carefully drew the diagram, this will give us a good sense if our answer does indeed make sense. Okay, so the next thing, we're going to straight away make our vector chart. So we have our three columns. We have our vector, which will be the individual vector diagram, our X component column, and our Y component column. So let's start off with vector A. Now, vector A is 100 kilometers per hour east. So that already means that vector A is already in the x-axis. There is no y component. So to represent that, looks like this. Our AX is equal to 100 kilometers per hour. And again, I'm just dropping the vector notation for the sake of convenience. But remember, sorry, not the vector notation, the number of sig figs. Just remember that the final answer has to represent the appropriate number of sig figs based on the given information. So this is moving towards the east, which means that our y component, our AY, is 0 kilometers per hour. Not a tilde, my bad, but a harpoon. That means the 0 vector. All right, vector A, done. Moving on to vector B. Now with our vector B, the key to drawing this is based on the order in which the directions were given. So since it said north 45 degrees east, we draw our northern component, then our eastern component. So we go north, then east. So there is our y component of vector B, there's our x component, and that is vector B itself. So that is our vector B. And remember, we dash the things we're looking for. So in this case, we are looking for these components, our by, our bx, and this angle down in here, that is our theta b. Magnitude of 45 degrees, an angle of 45 degrees, my apologies, and the magnitude of vector B is 500. Based on this, theta b is always at the tail of vector B, So we have to decide whether or not we are going to be using sine or cosine. Well, bx in this case is the opposite side, and by is the adjacent side. This means that the x component is associated with sine. So that'll be b sine theta b. Now we're going to do something maybe a little bit different than compared to last year, but I find that to avoid having to do excessive rounding, I like to leave it in this semi-algebraic form. And also, sine of 45 is associated with our special triangles. And sine of 45 is the equivalent of 1 over root 2. So our bx as a vector is 500 over root 2 kilometers per hour east, following through with our by. Our by is associated with the cosine function. So by is equal to b cos theta b, which is 500 cos of 45 degrees. And that reduces down to 500 over root 2. So by as a vector is 500 over root 2 kilometers per hour, and that is north. And finally, vector c. Our vector c is already in the y-axis. So our cx is going to equal 0 kilometers per hour as a vector, and our cy is 100 kilometers per hour north. So now we can actually find our resultant totals. And maybe I have enough room here. Let's see. So we have Rx is equal to AX plus BX plus CX. They're all collinear. So dropping the vector notation, our AX is 100 kilometers per hour towards the east. The east means positive, so that is going to be positive 100. And yes, you need to put the plus sign there. That communicates that you recognize that the direction is positive because it is going east. Vector B is also, BX I should say, is also going east, and it's 500 over root 2. So this is let's try that again. Positive 500 over root 2, and then plus CX, which is 0, not plus or minus, just 0. Now it's a debate what we can do here, and it all really depends on time. For example, if you're in a test situation, it might make most sense to actually just evaluate this numerically by putting in your calculator and rounding it off to, and I wouldn't just use 3 sig figs. Generally, what I like to do is if I have to use a decimal number, I tend to use 2 additional sig figs beyond what the final answer is going to be. So for example, let's say I had our data was in 3 sig figs, then I would carry 5 sig figs just to minimize the amount of rounding error. Or what we can do is we can continue on using algebraic techniques and then finding a common denominator. Well, the common denominator here would be root 2. So I'd have to multiply this 100 by root 2 over root 2. So this would be 100 root 2 plus 500 over root 2. And that makes it positive. I didn't say this is pretty, but it does prevent rounding. Now, for the sake of your sanity and mine, we get positive 453.55. So carrying 2 extra sig figs, kilometers per hour. And since we're on the x component, that works out to 453.55 kilometers per hour to the east. Now solving the y component. Same equation, just the subscripts change to y. Dropping the vector notation, our ay is equal to 0. Our ay is equal to 0. Our by is going to be positive because it is going north, 500 over root 2. And I just realized the goofy mistake that I made. Cy is not 100, it's 75. Well, at least I caught it now. I'm sure some of you have been pulling out your hair ever since I wrote that, and I am not going to re-edit the video. So I apologize for the anxiety I may have caused you for that little blunder, but we got it sorted. These are the sort of things that happen. Okay, so now common denominator is root 2 again. So I'm going to multiply the 75 with root 2 over root 2. So I get 500 plus 75 root 2 all over root 2. That looks gross. And this gives us 428.55 kilometers per hour. It is positive. So as a vector, that is Ry is equal to 428.55 kilometers per hour, and that would be north. Okay, so next, now that we have our Rx and our Ry, The next step is to draw the new, back up. Start with the new vector equation followed by the new vector diagram. So r is equal to rx plus our ry. Now we draw our new vector diagram. And remember, we have to start with a rx followed by the ry. So looking at our values, our rx is east, our ry is north, and our rx is larger than our ry, and that should be reflected in the diagram. So there's our rx, our ry, and our resultant. Now notice that the resultant in this case is now dashed, and the reason why is because rx and ry are actually known now. It's the resultant that is unknown. So generally speaking, the vector that is dashed or vectors that are dashed are unknown values at the point. And there's our theta r. Next step is to find the magnitude of the resultant. Thankfully, Pythagorean theorem is our friend because we have a right angle triangle. So the magnitude of r is equal to the square root of the magnitude of rx squared plus the magnitude of ry squared. Dropping the extra vector notation, substituting our values in. And again, remember, since we're dealing with magnitudes, we don't include all the decimal places. My apologies, not all the decimal places. Sorry. We don't include the plus or minuses. There we go. Not thinking straight here. Apparently can't walk and chew gum at the same time. So 453.55. Now that's the x component. And it should line up with the x component here. So 453.55 all squared plus 428.55 all squared, which gives us 623.9936 kilometers per hour. And that is just the magnitude. And of course, in the final answer, we're going to have to round off to the 3 sig figs. So therefore, the magnitude of r is equal to 624 kilometers per hour. Final step is to solve for the angle. So now we have to find our theta r using tangent. Tan theta r is equal to the magnitude of ry over the magnitude of rx. Theta r is equal to the tan inverse or arctan of ry over rx, which is 428.55 divided by 453.55, giving us a value of 43.3766 degrees, or rounded off to 3 sig figs, 43.4 degrees. And finally, our therefore statement. Therefore, our resultant, actually, let's use the proper notation now. Therefore, B's velocity with respect to the ground, the second plane's velocity with respect to the ground, is going to equal to 624 kilometers per hour. And looking at our diagram, it's east then north. So east, 43.4 degrees north. And we're done. And just to confirm, I did mention that the resultant should be larger than 500, and it is. And the angle should have been slightly under 45 degrees, and it is. I tell you, folks, the component method is a thing of beauty. Sample problem number 4 in relative motion. A boat is moving at a speed of 50 kilometers per hour with a heading of due north with respect to the water. All right, so let's start highlighting some of the key things. So first of all, we're talking about a boat here, and we know that it is moving at 50 kilometers per hour. Now, here's the thing that's purposely misleading. It says speed, but it does state that we have a heading that is due north. So we actually do know both the magnitude and the direction of the boat's velocity. Now, the key thing is that velocity is measured with respect to the water. So this value right here, this 50 kilometers per hour, is referring to the boat's velocity with respect to the water. Next, the boat is traveling through a current. All right, so we're talking about the current in the water, of course. And that current is 7 kilometers per hour west, 30 degrees south. So the motion of the water is measured in comparison to the land. And that's how water currents are measured. Just the same way with airplane navigation when we refer to the wind velocity. The wind velocity is always stated relative to the ground. The same thing applies for currents in the ocean, in rivers, and lakes. It's always in reference to the land, which is quote unquote fixed. Now, if you can throw a ball with a maximum speed of 60 kilometers per hour. Now, here's the thing. Got to think about this. Where are we located? We're on the boat. So the ball is being thrown from the boat, which means that that 60 kilometers per hour is relative to the boat itself. What angle, let's highlight that in green, what angle must you throw said ball in order to hit a stationary target that is, now this is key, the target is due east. Okay, so let's figure out what this all means. A couple of issues that we have to clarify. We need to use symbols to represent each object with the relative motion. I think B for boat is fairly obvious. Now for the current, it is the water, so I'm going to use W instead of C for current. I'm going to use W. The land, I'm going to use G for ground. You can use shore if you like, but I generally work with G for ground. Now the next thing, the ball is being thrown. The problem is the ball starts with the letter B, just like boat. So we can't recycle B twice. So we have to use a unique identifier. So in this case, I'm going to choose P for projectile. It seems to be reasonably logical, but I mean, effectively any letter that makes sense works. So we know that this projectile is being launched from the boat with a speed of 60 kilometers per hour. Now we know the speed of it. The question is, what angle must we throw said ball? So really what we're looking for is the throwing angle of that projectile. What do we mean by the target that is due east? Well, what that means is that the projectile actually has to have an effective motion that is perfectly due east. Since you are throwing it from a moving object, the angle that you're going to have to throw this thing at is definitely not going to be due east. And here's the reason why. And let's see if we can just sort of illustrate this off to the side. Okay, so very obviously, let's say this is our projectile. And if the projectile was on a surface that was not moving, launching the projectile due east would cause the projectile to move in that direction. So the projectile's motion with respect to the ground would actually be due east in this particular case. But that's not what's actually happening here. So let's move that off here for a moment. So let's talk about, and we won't complicate it too much. So let's just say that the boat that we're on is moving north, and I'll use blue to represent that vector. So if we throw the projectile exactly due east, all right, so this is the vector representing the throw. So this is the boat's velocity. This is the projectile's velocity. Well, we would have to do the following thing. And here I'll shorten up that the boat's velocity there. The two velocities would add together. So our resultant velocity, and I'll just sketch that in red, would actually be this. That's the problem. Okay, so now what we want is we want the actual resultant velocity to be due east because we want it to actually move east with respect to the ground. So let's move this away, and this is our throw, and the angle of our throw can go any way. So we know that the boat, its velocity, and this is not in the example that we're actually doing. This is just a pre-example just to explain the idea. So what we know, and let's move that off to the side here, is that our desired resultant direction has got to be east. Okay. Now we know that the boat is heading north. So we're going to do that head-to-head thing. And then, of course, our throw is going to have to be something like that. Now, this makes sense. Now, the reason why, if you think about it, this black vector has an east component and a south component. And to give you an idea of what's happening here, we'll thicken that up a little bit. And then I'm going to draw the components. And the reason why I want to draw the components of the throw is that you can get a sense of what's happening here in terms of the overall motion. So again, the red vector represents the resultant velocity. This blue vector represents our boat. And I guess, and like I said, we're ignoring the current right now because we just want to simplify just so we understand the concept here. So now what I'm going to do is I'm going to draw the y component of that throw and then the x component of that throw. And what you can see is that the x component of the throw is what actually gives us our resultant. And it's our y component of the throw that cancels out the boat's motion. That's the point. Because what we're trying to do is we're trying to prevent our projectile from drifting north when we throw it, which means we have to have a large enough component going south to compensate for the motion of the boat going north. And that's the big idea. So the remaining component, the X component, is how the projectile will actually move with respect to the ground. So that's the idea in a nutshell. And of course, what we're trying to find is what this throwing angle is. Now, our question is a little bit more complex because we have a bunch of things in addition to consider. And that specifically would be the ocean current or the river current or wherever we're throwing it from. All right, so let's start off with the nomenclature. So we know we have a boat and it is moving at a speed of 50 kilometers per hour with a heading of due north. All right, so that is the boat's velocity, and try to make that subscript a little bit more subscripty. The boat's velocity with respect to the water, and that is 50 kilometers per hour north. Now, the boat is traveling through a current of 7 kilometers per hour. So I'm using W for the water. So that current is the flow of the water. So that's the water's velocity with respect to the ground. And that is 7 kilometers per hour west, 30 degrees south. The next value is the magnitude of the projectile's velocity with respect to the boat. So this is going to be our PVB. But we have some missing information. We do not know what the heading is. So that value is unknown. What we do, however, know is the direction of the resultant. So we know that the projectile's velocity with respect to the ground, although has an unknown magnitude, it does have a known direction, which is east. So what we're looking for is this angle right here for the projectile's velocity with respect to the boat. So we're looking for the heading of the projectile. Now it'll be more clear what vector that is, or what angle that is, I should say, when we make our vector equation and, of course, the short names for our vectors. So that's, again, what we do is we always start with making the vector equation. So the key thing is we have to remember which vector is our resultant. And our resultant in this case is the PVG. So let's start with our vector equation. So we've got PVG. Okay, so going through the process. So the first thing we have to do is on the right-hand side, our first vector must also start with the letter P, and that is our PVB. So we start off with our PVB. Of course, our next vector has to start with the letter B, and that would be our BVW. And then our next vector must start with the W, and that would be our WVG. And all vectors have now been accounted for, and the pattern worked because our last vector has to end with a G to match. So we start with the P, start with the letter P. We have the B sandwich, then a W sandwich. Just change my highlight colors there. So we start with the P, we got our sandwiches working out, and then ends with the G. So we're good. Now that we've successfully created the vector equation, we now go with the short names. So PVG is our resultant. PVB is our vector A, PVW our vector B, and our WVG is our vector C. So let's go back into our givens and retroactively label everything. Now that everything is labeled, what we then realize is that the angle of PVB is going to be the angle associated with vector A. So this theta heading of the projectile is actually our theta A. So that's what we're looking for. Clearly, we're going to have to do component method because it's not going to make a triangle. So we're going to have to do the vector chart and all that business. But in this case, it is very important that we start off with the vector equation, diagram, I should say. I know, typically when we do component method, we don't have to usually draw the vector diagram first. We can usually jump right into the chart. But the issue is the unknown value for the angle of vector A. So at the moment, we don't know which directions those components are going to be. So we don't know if the X component is going to be east or west, or if the Y component is going to be north or south. I mean, if you think about it carefully, you probably could figure it out, but here is a systematic way of making sure that you get it right. So again, when we draw the vector diagram, in this scenario, when we don't know the direction of one of our vectors, we have to use that technique where we start off with the vectors we know everything about. So in this particular case, the two vectors that we know everything about are vectors B and vector C. So the very first thing that we sketch will be vectors B and C. Then we move on to the vector for which we know the direction. And then finally, the last vector will just fall into place, just like completing a jigsaw puzzle. Okay, so let's start with this vector diagram. So we're going to start off with vectors B and C. And since some of these vectors are not playing nice, or nicely if we want to be grammatically correct, we are going to have to work with our compass roses. So starting off with vector B, that's 50 kilometers per hour north. And again, make sure that you make your diagrams significantly large. General rule, they should take up about a quarter of the page if you want to be effective in terms of being able to label them clearly. Next, to draw vector C, we will need to generate a compass rose because the components of vector C is west, then south. So there's our compass rose. And I was negligent. I forgot to label this as vector B. Now again, be sensible. Vector B has a magnitude of 50. Vector C only has a magnitude of 7. It's only slightly larger than a fifth of this vector. So again, you don't have to be 100% exact with those measurements, but make them reasonable. And again, it's also west 30 degrees south. So don't draw it at a 45-degree angle, something like that. Okay, so that's our vector C. And this angle in here, that's 30 degrees. Next is the resultant, and that's because we know the direction. So we don't know the magnitude, but we do know the direction. So we know that it's going to go east. And we know that the resultant attaches head to head with the last vector and tail to tail with our first vector. That is always the case. So when we draw our resultant, and I clearly did not give myself enough real estate, this is why your teachers always strongly recommend you use pencil so that if you have to erase things, it's a little bit easier to do instead of using mountains of whiteout. Sketching in our resultant, it is going to be east. We don't know how long it is. And truthfully, it's not super important to get the lengths exactly right. We just have to get it reasonably close. And of course, we need to make that dashed. And then finally, vector A can only be drawn one way. Vector A has to start from the tail of the resultant and attach to the tail of B. Perfect. So this gives us a very good sense now of the directions of the components for A. A is going to have a component that goes east, and A is going to have a component that is going south. And I am going to draw it so that my theta A is attached to the east line. So when we draw the components for vector A, we're going to have an east component, then we're going to have a south component. So adding the labels, we've got our vector, which is our vector diagram, our x comp, and our y comp. So we're going to start off with our vector A. So when we look at our vector A, we know that we're going to have, an east component, and then we're going to have a south component. So that's our vector A, that's our theta A, our AX, and our AY. Again, theta A is what we're trying to find. And the magnitude of A, that's 60. So the x component is going to be related to the cosine. And the reason being is that this is the adjacent side and AY is the opposite side. So the x component is associated with cosine because of adjacent. So this is going to be AX equals A cos of theta A. Our AY is going to be equal to A sine of theta A. So what I'm going to do is I'm going to do some partial substitution. So kind of a hybrid algebra version. It's not fully algebraic because we're going to replace some of the letters with the values themselves. So AX is equal to 60 cos theta A, which is what we're trying to find. And we know that it is east. So I'm going to put in the direction here. And I realize I'm not going to put in the units because it's unnecessary and it just makes it sloppy. And we're going to make that a vector. So we have to make sure we get the harpoon and draw the harpoon well. And with the y component, AY as a vector is going to be 60 sine of theta A, and it is south. So the AX component, when we substitute into the resultant equation, will be positive, but the AY will be negative. Now we focus on vector B. Vector B is the 50 kilometers per hour north. It's already in component form. So in this case, our BX is 0 kilometers per hour, the zero vector, and our BY is 50 kilometers per hour. And again, and the direction. And again, in these interim steps, I don't keep all the sig figs unnecessarily just to reduce clutter. But we have to remember at the very end, we have to round off to the appropriate number of sig figs, in this case, 4. And the goal is ultimately to work with the least number of rounded values as possible. So that means that we're going to try to use this hybrid algebra form for the most part, as far as we can take it. Next is our vector C. And our vector C has a west component followed by the south component. And again, this is a common mistake, is that you have to read it in the order. So if it's west, then south, you're going to draw it west, then south. So these are the components, and this is actually vector C. Now again, in this case, the components are unknown. That's why we dashed them. That will be our CX. That will be our CY. This is our theta C. We know that angle is 30. We know that magnitude is 7. And I suppose up here I should have been consistent and labeled that as 50. Again, our CX is on the adjacent side. So our CX is equal to C cos theta C. Our CY, therefore, will be C sine theta C. So this will be, as a vector, 7 cos 30 degrees west. Now, 30 degrees is a special angle, and the cosine of 30 degrees is root 3 over 2. So we're going to replace this cos of 30 with root 3 over 2 to clean it up even further. So this gives us 7 times root 3 over 2. You know what? I regret doing this. I'm going to take the harpoon off, and I'll put the direction on the last line. Should have thought ahead, but I didn't. Okay, so now this reduces to... Now, leaving it like this, and this is a judgment call, leaving it as a fraction is harder to substitute in, but also 7 doesn't divide evenly by 2, but you don't have to round it because 7 divided by 2 is 3.5. So that's a reasonable amount. Okay, so this gives us 3.5 root 3, and now we can report the direction, which is west. And I suppose I should still put the units in there. Okay, so now CY, that's going to be 7 sine of 30 degrees. Well, remembering your special angles, sine of 30 degrees is 1/2. So therefore, our CY in this case is going to be 3.5 kilometers per hour south. Let's just double check. Yep, looks like we're good. Now time to focus on the resultant. Now we know the resultant is exactly east. So I'm going to steal that diagram and we'll shrink it down a bit. So here's what this implies. This is the thing about the resultant. There is no y component. So what we know is this, is that our x component is actually equal to the resultant, and the y component of the resultant is equal to the zero vector. That's very important, this little distinction here, because that is necessary to complete the next steps. We have to know what's going on with Rx and Ry. This would be a good time to remind us of what we're actually trying to solve for. In this question, we're not actually trying to solve for the resultant. We are trying to solve for our theta A. Well, we've got theta A both in the x-axis and the y-axis. So it looks like there are two possible ways that we could go about solving for theta A. So we'll start with the x component of the resultant. Rx is equal to ax plus bx plus cx. So we're going to drop our vector notation because everything in the x-axis is collinear. Our Rx is really just our R, so that equals R, and it's positive because it's going to the right. Now our Ax is east, and it is 60 cos theta A. So I'm going to substitute in positive 60 cos theta A. Our Bx is 0, and our Cx is west, so that will be negative 3.5 root 3. We'll do a little cleanup here. So this is r 60 cos theta a minus 3.5 root 3. I'll call this my equation 1. Well, looking here, let's see if we can proceed. We have to solve for theta a. What's the issue? We don't know the value for r. We can't solve for theta a unless we find the value for r. So this appears to be a bit of a dead end. But don't despair. We have the y component still. So let's move on to the y component, and maybe that will inform us a little bit better of how to proceed from there. So going with the y component, ry is equal to ay plus by plus cy. Now our ry, if you recall over here, is equal to 0. So we can replace this with 0. Now let's focus on what's happening with ay. Well, ay is equal to 60 sine a and south, which makes it negative. So negative 60 sine theta a. Our vector by is 50 kilometers per hour north, which makes this a positive value, positive 50. And then finally, looking at cy, that's south, making it a negative number. Let's clean things up. And now it looks like we're in good shape here. We're only down to one variable now, and that's because our y component was 0. So it looks like we can just continue on from here and solve for our theta a. And let's do that. So I'm going to bring this term to the left-hand side. So this gives me 60 sine theta a is equal to 46.5. Our sine theta a is 46.5 over 60. And looks like I'm going to have to give myself a little bit more real estate here. Admittedly, this is one of the advantages of working with OneNote. You can't exactly do this with a whiteboard or a chalkboard for that matter. Isolating for theta a, that will be equal to the arcsine or sine inverse of 46.5 over 60, which gives us a value of 50.80503257 degrees, keeping all that calculator vomit. And now that we have that angle, we can finally report the direction. So that's our angle, theta a. And if we look on the vector diagram, the way we drew it, we went east, then we went south. Therefore, the heading of the projectile's velocity with respect to the boat is equal to east, and we have to round off to 4 sig figs. So that'd be east 50.8. Now, this is a good one here. Your rounding rules. Let's take a look. So since I'm rounding off to 4 sig figs here, I'm going to put my rounding line there. Some of you will remember that, oh, wait, when we have a 5, we either, we use that rounding, the banker's rounding, and you see this 5 here, and it's like, oh, okay, so we have to make sure that the remaining value to the left here has got to be even. So the tendency is you're going to say, oh, well, since that's a 5, we're going to keep that as a 0. But you can't because you're forgetting all of these digits here. So this actually isn't ending on a 5. This is past 5. So when we round, we have to round up. So that'll be 50.81. If this was 5 followed by a bunch of zeros, sure, you would round down. But since it's 5 followed by a bunch of other values, it's past the halfway point. And as a result, we round up. So that makes it east 50.81 degrees south. And again, it's one of these questions that looks very involved at the very beginning. But if you follow the systematic approach to solving it using the basic algorithms that we always use, you'll find that these questions are less daunting than they initially look at first glimpse. Our next sample problem, however, adds a shockingly significant layer of complexity with what appears to be just a very trivial minor change. So that one's coming up next. Example 5. This is what I refer to as the Uber to the epic relative motion question. Despite the ridiculous title, it's a pretty good question because of the unexpected difficulty with it. So let's just take a quick look. A boat is moving at a speed of 50 kilometers per hour with a heading of due north. Wait, this sounds exactly like the last question. With respect to the water, the boat is traveling through a current of 7 kilometers per hour, west 30 degrees south. Wow, it sounds exactly like the last question. Weird. If you can throw a ball at a maximum speed of 60 kilometers per hour, same question as before. How is this any different? At what angle must you throw said ball in order to hit a stationary target? Ah, there it is. Right here. East, 10 degrees north. That really does seem like a very minor change Funny, however, how this minor change does actually create a fairly significantly difficult situation in terms of the algebra if you don't have a solid technique. So there are a number of solutions to this problem. We're going to take a look at a couple. But first, let's do our given and RTF. And essentially, it's the same as the last one. So all I'm going to do is steal the information from the last question, but modify it for this one. Okay, here we go. So I basically copied and pasted everything from the last question, but we do have to do a modification. All these vectors remain the same except for our resultant. And with our resultant, it's the direction that has changed. So to modify this, east 10.00 degrees north. And again, it really does seem like a trivial change. It's just you're changing it by 10 degrees. How does that make it so much more worse? Well, you're about to see. And as you can see, the vector equation is the same thing. We have the same short names, and we're looking for the same thing, the heading of the projectile. The next step is to draw the new vector diagram. And most of the vector diagram we can use from the previous one, but there is a couple of changes that we have to address. Or I should say there are a few changes. All right, so we've copied the portion of vector B and vector C because that's the same as before. So again, we start with the vectors that we know everything about. We know the direction and magnitude of vector B and vector C. The issue, of course, next is once we've plotted those two vectors, the next one is we go with the vector for which we know the direction, which is the resultant. But in this case, the resultant is east 10 degrees north. So we kind of need to do a bit of funny business with the compass roses here. So I'm going to take this compass rose and I'm going to paste it here. And then we're going to need another one for the resultant. So I'm actually going to just put this off to the side here and then I'll move it into place because our resultant is no longer just east, but it's east 10 degrees north. So our resultant is going to look like this and 10 degrees north, something like that. All right, so now I'm going to move this into place and I'm going to have to put my compass rose on a diet here a bit. Okay, so there's our resultant. And of course we have to dash it. And this little tiny angle in there, that's our theta r. And actually, we'll just label it with the actual degree. And that is 10 degrees right there, that little tiny 10 degrees. Now I got to adjust this compass rose there. That's a little bit better. There we go. Okay, so drawing the diagram is tricky, much easier to do on the computer. Now, vector A. Same deal as before. We know that vector C is head to head, just like we have up there, and then tail to tail with vector A. So let's draw in our vector A, and it's going to attach to the base of vector B. And there we have it. So this angle in here, that right there is our theta A. Now, notice the theta A, and I'm going to zoom in good and tight here. The theta A is measured against the east line here, not the resultant. And that's very important. So do not conflate this entire angle here with theta A. Theta A plus 10 degrees is this entire angle. We're only looking for theta A. My diagram is a little off kilter here. I didn't notice that. There we go. Probably when I shifted everything. Anyway, okay, that looks a little bit better. I think we're good now. Okay, so next we're going to copy our vector chart over, and absolutely everything is the same for vectors A, B, and C, but what's different is what's going on with the resultant. So I basically copied everything that we did initially. No sense in having to reinvent the wheel. But now what we have to do is we have to address what's going on here and here. And this is where the complexity comes in. Once again, we're gonna sketch our resultant. Now, I know it's only 10 degrees, and for accuracy, I understand that the desire would be to draw it as 10 degrees. However, for the convenience of the diagram, especially labeling, I'm going to exaggerate that angle. Sometimes that is necessary for clarity. So obviously, that's way bigger than 10 degrees, and this is our resultant R, which we don't know. We're going to dash that, and then this resultant also has its x and y components, which are also unknown. And for the sake of clarity, I'll just keep them. I'll keep the x and y components a little bit thinner. There's our ry, and there's our rx, and this here is our theta r. but that is a known angle of 10 degrees. That's the only thing that is known. What makes things a little bit more complex is what's going to be happening with the Rx and Ry components. Now I'm just going to shift this up because I know I'm going to need that real estate. So again, copying over from the last example, we got positive Rx is equal to positive 60 cos theta A minus 3.5 root 3. Again, basically like the last problem. The difference is this is no longer R, this is Rx. Now we have two unknowns. We're trying to find theta A, but we don't have Rx. So we're in a bit of a dead end. Now let's take a look at the Y component. All right. So now that we've copied that information, what's different is now this value for Ry is not 0. So here is our problem. I'm going to highlight all the unique unknowns. So we've got our theta A, so that's one unknown. Then we have our Rx, that's two unknowns. And now we have our Ry. So that's three unknowns. When you have three unknowns, you need three equations. You also need to put a 6 here so it doesn't look ridiculous. Okay, missing some details here. Okay, so again, since we have three unique unknowns, Rx, Ry, and theta A, that means we need at least three equations in order to finish the solution. Step 1 is I'm going to deal with the Rx and the Ry situation. And what I want to do is I want to eliminate the number of unique variables down to eventually 1. As far as Rx and Ry goes, we can actually express them both in terms of R. And how we can do that is the fact that we have a known 10 degree. We know our theta R is 10 degrees. So using the primary trig ratios, I'm going to express Rx as R cos theta R, and that is east. And Ry is going to be R sine theta R north. And the important thing to note is that theta R is not a variable, but a known value of 10 degrees. However, I'm going to work with theta R. There's a reason. Normally, I would just leave it. I would put the 10 degrees in there to do that sort of quasi-algebraic method. But by leaving the theta R in there, hopefully that will guide you to the next part of the solution. So what we're going to do next is we're going to replace our Rx with positive R cos theta R, and that is equal to positive 60 cos theta A minus 3.5 root 3. And let's call that equation 1. Now we're going to do the same thing with our Ry. And now we have R sine theta R, specifically positive R sine theta R, is equal to negative 60 sine theta A plus 46.5. So one of the things that we're going to do is eliminate as many of the unknowns as we can. Well, by doing what we just did, we've now reduced it down to two unique unknowns. So both equations have an R, and both equations have a theta A. And a reminder, the theta R is not unknown. It's 10 degrees, but we're just leaving it as theta R for reasons that are yet to be revealed. So as I've mentioned before, there's actually several ways that you can solve this. I'm going to pick two. So the first thing that I'm going to do is I am actually going to isolate for R in both of these equations. So that's going to give me R is equal to 60 cos theta A minus 3.5 root 3 over cos theta R. And we'll call that 1b. And we'll do the same over here. R is equal to negative 60 sine theta A plus 46.5 over sine theta R. And we'll call this 2b or not 2b. Yeah, okay, that was lame. All right, now, so we're going to do the good old process of elimination. So I'm going to set these two equations equal to each other, and that way we can get rid of the R. So let's get up here where we have a little bit more real estate. So we're going to set 1b equal to 2b. Okay, things are getting very ugly because we need to isolate for theta A, but here's the problem. Cos theta A and sine theta A are two different functions. So when I said that we had three variables, that's technically correct, but it's kind of like four actually, because cos theta A and sine theta A are quite different. So we actually have to reduce this down to a single trig function. So having these two separate trig functions, they behave just like unknowns, and that's kind of gross. Again, a reminder, theta r is known, so cos theta r is just a number. Sine theta r is also just a number. And again, to add to the nightmare, we have fractions, and fractions are terrible. So we are going to remove the fractions, and to do that, we are going to cross multiply using distributive property as well. So it's about to get really, really algebraic in here. All right, so let's do this. So I'm going to bring our sine theta r and then the cosine theta r over to the right-hand side. And we have to use distributive property. So I'm going to distribute this sine function onto these two terms and this cosine function onto these two terms. This gives us 60 cos theta A sine theta r minus 3.5 root 3 gross sine theta r. And I'm already going to run out of real estate. So I'm going to move this over like this. Let's tighten that up a bit. There we go. And then we get negative 60 sine theta A cos theta r plus 46.5 cos theta r. Yes, it's getting more and more terrible as each line progresses, but we're just going to keep going. Now that we've got rid of the fractions, what I'm going to do next is I'm going to collect my terms of concern. This term has the cos theta A, and this term has the sine theta A. Since the theta A is the thing that we're looking for, we're going to get the theta A terms onto the same side. So what that means is I'm going to bring this term onto this side, and I'm going to bring that term onto that side. This may look like we're not any closer to a solution, but I promise you we are. And some of you might be having a bit of an inkling of what's coming, and you might not like it. So clearly there's going to be some trig stuff involved here, and perhaps getting rid of these 60s on the left-hand side might help the process along a little bit. So what I'm going to do is I'm going to take a common factor of 60. Well, actually, you know what I'm going to do? I'm going to do this instead. I don't really need to take a common factor. What I need to do is divide both sides of our equation by 60. And if I do that, if I divide both sides of the equation by 60, I can eliminate those 60s there. Because remember, when you divide the numerator by the denominator, all terms in the numerator have to be divided by that. So that works out perfectly. I could have done a common factor and then brought it over, but why mince words? Let's just get it done. So now we have cos theta A sine theta r plus sine theta A cos theta r equals all of this. And if you don't recognize it, I will highlight the important thing here. And I suppose you're all pretty excited to see what I just pulled up here. That's correct. The table of trigonometric identities. So we're going to scroll on down here and we're going to take a look at the sum difference formulas here. And if you look carefully, and let's switch back. So we've got a cos of one angle, sine of the other, plus the sine of the first times the cosine of the second. So cos and sine and cos, and sine and cos and sine. It is the sum difference formula. It is this one right here, the very first one. So we can replace this expression here with this function here. So this is the sum difference trig identity. So we can replace all of this with sine theta A plus theta r. And that was the tough one right there. Having to recognize that you needed to use a trig identity to solve this problem. And as I mentioned before, a simple difference of adding that 10 degrees made the question so much more complex. But now solving it is a trivial affair because we only have a single trig function that we need to undo, take the inverse of. Again, as a reminder, sine theta r and cos theta r are just numbers because we have the value for theta r. So we're going to take the arcsine of both sides, or sine inverse if you prefer. And then we are going to isolate for theta A. And now we're going to substitute in for our values for theta r, which gives us a value of theta A of 41.33120133 degrees with all the calculator vomit. So now our concluding statement. So it's still east, then south. So therefore, the heading of the projectile's velocity with respect to the boat is east 41.33 to 4 sig figs degrees south. Next is an alternate solution to this problem, which mercifully is significantly less difficult. Now let's take a look at an alternative solution to this particular problem that will not have to involve using any trig identities or excessively complex mathematics. So the first step is to identify the issue that made this so much more difficult. Now, here is the diagram in question 5, and it had everything to do with what was going on with the resultant. This is what made the problem. Allow me to elaborate. In example number 4, our resultant sat exactly along the east line of the compass rose. And because of that, this was possible. Our y component was equal to 0. The fact that we were able to zero out one of the components of the resultant made the mathematics much easier, because once we were able to substitute a 0 in here, then that meant that we only had one variable in this equation, which made solving this a rather trivial affair. That 10 degrees really messed everything up. So here's the big idea. If we could somehow fix our resultant so that it sat on one of the branches of the compass rose, so either sitting on a north line, east line, south line, or west line, then we could avoid having the complexity of these two equations with two disparate trig functions, which required us to use trig identities, and it was just largely unpleasant. So we actually can do something about this. So we're going to pop into another program and show you what I mean. So I'm taking this diagram and we're going to paste it. Okay, so this is just a Google Draw document. And this is our original diagram for question 5. What I'm going to do here is I'm going to add a horizontal line as a guide here. So the horizontal line represents the true x-axis. To fix this problem, we can basically rotate the frame of reference. Here's what I mean by this. Basically, before we even start the question, we can take this whole frame of reference and rotate it by the 10 degrees. And if we do that, that means our vector, our resultant, is actually now sitting perfectly on the horizontal, which means it eliminates the y component. And that makes the mathematics as easy as it was in example number 4. But what this means then is that we have to actually rotate every single vector by that amount. So essentially, what I did is I rotated the whole frame of reference by 10 degrees clockwise, which means every other vector has to be rotated by 10 degrees clockwise. Once we do that, then we can do the math just like we did in example number 4. But the trick is this, and this is very important. You have to ensure that after you have done that, that you do not rotate the angles back until you're done all the mathematical analysis. So the mathematical analysis that you'll be doing is in this rotated frame of reference. Once you calculate all the numbers, only then do you rotate back. So let's pop back into OneNote and take care of that problem. So here's the concept, now spelled correctly. To more easily solve this question, we can rotate the entire frame of reference so that the resultant lines up with the closest arm of the compass rose. Not roses. So let's come up to our diagram. So when we look at our compass rose, that's our north arm, east, south, and west arm. As you can see in our particular example, the resultant is closest to the east arm, which means we're going to rotate everything 10 degrees to the east. And this way, our resultant will now sit perfectly on the x-axis in the rotated frame of reference. So in our case, we're going to rotate the entire frame of reference 10 degrees clockwise. That means every single vector has to get rotated first. Then we do the math, and then from there, we get our conclusions, and then rotate back. So here's our given from the original frame of reference. And next, we're going to rotate 10 degrees clockwise, taking a look at vector B. In the original frame of reference, we were north. Now, if we rotate 10 degrees clockwise, my apologies. I'm going to actually just, for the sake of clarity, I'm going to drop a little compass rose here and use it as a little model to help us determine the correct orientation. So here is my original vector B, which is pointing north. Now, clockwise is in this direction. So if I rotate clockwise by 10 degrees, this angle in here is now 10 degrees. So our new direction for this vector is going to be north 10.00 degrees east. And let's make that a little clearer. Vector C in this original form was west 30 degrees south. Okay, so let's take this west. Let's try to get it aligned there a little bit better. There we go. So west, get it in a more visible position. 30 degrees south. All right, so it's going to look something like that. Now, we're rotating again 10 degrees clockwise, which means that we have to rotate in this direction by 10 degrees. So if this was originally 30 degrees and we go 10 degrees in that way, that reduces this angle by 10 degrees. So this 30 turns into a 20. And just so you can see it. So it's going to shrink by 10 degrees. So instead of west 30 degrees south, it is now going to be west 20 degrees south. Now with our vector A, we are still unknown in terms of its overall direction. So it's still going to be a question mark. And finally, looking at a resultant. So our resultant is east 10 degrees north. So we start east and then we rotate 10 degrees north. Okay. And of course, if we rotate 10 degrees clockwise, that clockwise takes us to east. So our resultant now is east. But just to clarify, our vector A, in our original equation or in our original question, our vector A had an east and a south component. And I should actually label A there. So it has an east and a south component. By rotating it 10 degrees is unlikely to have it move past this south line. So it's still going to have an east and south component when we sketch it. So we can redraw the vector diagram with the corrected angles, and you should be able to see that. So I'm basically going to edit what we got right now. And through the magic of editing, I will make that happen in an instant. And there it is. There's our rotated vector diagram. So as you can see, everything has been rotated by 10 degrees, and now our resultant vector is perfectly aligned with the x-axis, which means that the y component is going to be 0. And now it's just simply using the component method again. And again, as the magic of editing allows, here's all the mathematics real quick. So our vector A, we established that we had an x component and a y component. There's our theta A, magnitude of 60. So as far as ax and ay is concerned, they stayed the same. Our vector B has its y component followed by the x component, and that's because it was north then east. So our bx is 50 sine 10 degrees towards the east. Our by is 50 cos 10 degrees towards the north. And with our vector C, it was west then south by 20 degrees. So that gives us cx is associated with cosine, cy associated with sine. And now we just jump into the resultant statements. So Rx is equal to Ax plus Bx plus Cx. Our Rx is equal to the resultant. Our Ax is positive because it's going east, 60 cos theta A. Our Bx is also going east, so that's positive 50 sine of 10. And our Cx component was west, so that makes it negative. And I called this my equation 1 here. And we actually used it this time to calculate the resultant. I didn't calculate it the last time, but I decided to calculate it this time. Then we look at the y component. So ry is equal to ay plus by. The ry is equal to 0, mercifully, which makes this much easier. Our y component for a is south, so that's why it's negative. Our by is north, which is positive. And our cy is south, which was negative. And we were able to isolate directly for theta A. and we get a theta A of 51.33120133 degrees. Now, please bear in mind, because you may not recognize that that wasn't the same answer that we got before, but remember, we're in the rotated frame of reference. So that means what we have to do is, now that we have that angle, we have to unrotate it. But this is very, 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 very important. This value here, this theta A in the rotated frame of reference, is the value that we have to use for the remaining calculations. So when we want to figure out what the actual resultant is, notice that it's this value for the angle. If you correct the angle back to the original frame of reference and then use that value in here, you will get the math wrong. And the reason why is that this entire equation here was developed on angles based on the rotated frame of reference. So by putting in an unrotated angle, it completely messes up the math. So you complete all the math while you're still in the rotated frame of reference. By doing so, we now have a magnitude for our resultant, which is 39.59361461 kilometers per hour. As a vector in the rotated universe, well, frame of reference, that is east. But when we report it again, we have to take it out of the rotated frame of reference. So let's fix our angle first. So we know that the heading for the rotated frame of reference is east 51.3 degrees south. We need to rotate back 10 degrees counterclockwise. I really do strongly suggest that you make a temporary compass rose to help make sure that you do rotate it correctly. So let's go with the original. So it's east 51.33 degrees south. So you take a vector east and then 51.33 degrees south, something like that. Now you're rotating 10 degrees counterclockwise. That means you're rotating this way. So if this originally in here is your 51.33 degrees, by rotating it 10 degrees counterclockwise, we subtract the 10 from this 51.33. And that's why a diagram really helps to make sure that you get the numbers right. Doing it in your head can cause confusion. So therefore, we get in the original frame of reference a heading of east 41.33 degrees south, which is precisely what we got using that first method. So finally, the therefore statement. Therefore, the heading is east 41.33 degrees south, and the projectile's velocity with respect to the ground is equal to 39.59 kilometers per hour east 10 degrees north. Because if you recall, that is the original resultant, direction of the resultant, which was in the given section up here. So our original projectile velocity with respect to the ground was east 10 degrees north. So I think you can agree that the second methodology of rotating your frame of reference to avoid using component method makes the question decidedly easier to solve. Technically, you can use whatever technique you wish, but I cannot more strongly recommend using this method of rotating the frame of reference so we can avoid the excessive mathematics. And that is the approach I would expect you to use on an assessment, simply because this is much faster.